back. So, last time we left off on Monday, we had done free body diagram. We were looking at like what is a spring going to do as something drops onto it, and got to the part where we had an equation of motion, and the question was like, okay, well, what happens to the block after it hits that spring? And the end result was that we have some kind of differential equation, ordinary differential equation. This one happens to be a linear ordinary differential equation, so it's super ordinary. Just your run-of-the-mill, see it every day. It's the Dunkin' Donuts of differential equations. What do we do with it? Who has like done differential equations before? Like, have you dealt with them? What do you do with like second order differential equations? What was your preferred approach? There's more than one way. Not. Yeah. You don't like Laplace transforms? Oh man, okay. Laplace, the nice thing about Laplace transforms is it takes all the calculus and turns it into algebra, which has its benefits. And if you have a stable system, you can jump right into Fourier transforms, assuming it's stable, but okay, Laplace transforms, but maybe not. Maybe we don't want to do Laplace. Other no preferred differential equations methods, I guess. That's what it sounds like. You've just been avoiding, hoping that they won't come back. Like, if you don't speak its name, then it won't, like, get you, Voldemort. All right, so let's take a minute, because almost every equation of motion is going to be a second order differential equation. It's just the nature of dynamics. F equals ma. If you're looking for position, a is the second derivative, so you end up with something where acceleration is a function of position, velocity, and time. Okay. I like to rewrite this as x double dot plus 1000x equals 9.81. Yeah. Where the dots, have you seen those dots before? No? Cool. We're trying something new then. The more derivatives you have, the more dots you have. Most of the time we'll only have 2 dots. If you're doing like higher order control theory, maybe you'll have like 4 dots or 5 dots, but yeah.
So is that just like a different way to mark it, like x prime or x double prime?
Oh, yeah. Okay. So like a lot of times you might see like f prime, like that. This one, sometimes those primes are df dt. Some people use them as, instead of df dt, it's like a partial of f with respect to x. So you, at least in a lot of physics, if you see a prime, it's a ddx. If you see a dot, it's always a ddt. The end, the ddt. So that's why I like the dots, because it's every time you see a dot over something, you always know it's a full time derivative, not like a partial space derivative. or even like a full space derivative or something. But yeah, and then a lot of times even these primes, as you get into like other fluid mechanics and solid mechanics and stuff, these get turned into f comma x to say like take this derivative over space rather than time, or an f comma t to say, or an f dot full derivative. Anyway, that's a lot of stuff. Mostly we're just going to deal with dots. Just dots over the x's, so we don't have to worry about these. Do we know what kind of function we expect from like x, as it, if we're saying x is like how far the spring displaces? Do we know, like, will it be a parabola, an exponential? Yeah. Oh, you think it'll decrease? Oh, yeah. Where would the decrease, where would like the loss in energy come from? I like, so intuitively it makes sense. Like if you hit the spring, it's not gonna elastically come back at us. But have we accounted for that in our free body diagram in terms of like what forces we have? What do we think? So the main thing of like, is this thing going to lose kinetic energy? So we're saying like it's gonna bounce. There's gonna be some kind of bouncing. If we are losing kinetic energy, then we need something in there that's called a non-conservative force. What is a non-conservative force? Like a libertarian force. It lives in Colorado, it smokes pot, but it also is like anti-rights for other religions or something, I don't know. Libertarian. That's non-conservative. Non-conservative would be things like friction, damping, drag, like anything that usually there's either a velocity dependence on it, so the faster you go, the bigger the force or something, or something where it's not. So conservative forces are all position based. So a spring, no matter what you do, if you stretch it, compress it, stretch it, and then compress it, the amount of potential energy you have just depends on the difference from where you started to where you ended. It doesn't matter how you got there. Versus friction, if I push a box out the door, it would be easier to go straight out the door rather than do a whole bunch of loops and then go out the door, because it's path dependent. So if you have any path dependent forces, like energy losses. So right now it's all conservative. Everything is GOP elephant style. Everything's conservative. So in that case, so if everything's conservative, what does that do to like that sinusoid kind of function? Do we need to change like decay? No? So some kind of sinusoid-ish? This is like the Cooper guess and check method. I know it's gonna be some kind of like sine. So let's guess. Do I know how big the sine wave is going to be? Like if I drop it from a higher height, is the amplitude bigger versus a smaller height? Maybe? Or is it always the same amplitude for a given spring? Do you know what I mean by amplitude? Crank it up to 11. Yeah.
If you drop it from a higher height, the amplitude is higher.
Okay, yeah, so there's got to be some kind of dependence on like what happened in the system. So let's say, I don't know what it is, but there's some kind of changing amplitude that depends on the system. What about the frequency of this sine wave? Is it going to be real fast? Is it real slow? Are all springs and all masses the same frequency? Like, do they always bounce the same way? Yep. Oh, heavier takes longer. Yeah, I like that.
It also depends on like the spring constant, like how much resistance the spring.
Okay, spring constant is going to be in there. And for now, we know, like, so the mass and the spring constant we definitely think are going to change it. For now, we can just say, like, it's going to be something. I don't know what it is. I'll call it omega. So I know it's going to be a sine wave. I know it's going to have this. So what is the derivative of a sine omega t? A is a constant, omega is a constant. We don't know what they are yet, but we can try to figure it out. Cosine, something with cosine. I know I'm asking you to do. It'll still be like a cosine omega t, right? Is the a gone? We derive that right out? No. Keep that one, okay? Is that all we need? A cosine omega t? Yeah, yeah, chain rule comes up a lot. Like, you have to take the derivative of what was inside the function, multiply that by. Does anyone see where I'm going with this? Or is this like, why the hell are we taking derivatives? Question. Alright, yeah, we're gonna plug all those back into the original equation. Nice. Does that tracks? It seems like a good idea. Alright. I've done it before. We're not gonna like, he lost control. We're going off the road. Alright, second derivative. What is that one? Omega squared, yep. Derivative cosine, negative sine. All right, so a negative sine omega t. So take the x double dot, put in a negative a omega squared sine omega t plus 1,000 times a sine omega t equals, I'm going to leave it as g. Did we solve the problem? Not quite, right? We're really close. And why do I say that? If this omega squared if omega squared is 1,000, then those two terms are 0. They add up to 0. Because it's a negative a sine and then a positive a sine with omega squared kind of pulled out. So let's do this. All right, now it's really stretching back into your memories. At least if you've done differential equations is not required for the course. We're not going to get into like all the different all the different types of differential equations, but we're going to keep dealing with second order, so we have to learn like at least a couple of things. Homogeneous and particular solutions. Does that ring a bell for anyone? What was the difference between a homogeneous and a particular solution?
Homogeneous is equal to 0.
Okay, yeah, homogeneous is solving the zero problem, which is what we were just saying like right here. Like if we can get this thing to equal 0, that would be our homogeneous solution. And then what's the particular?
Like C times one solution plus C times another solution.
It takes care of all the other stuff, right? Like it's the particular solution for whatever's driving that. So sometimes it's called the natural and the forced response. So when we said that it's going to be a sine function, that's the natural response of the thing. It's going to bounce and it's going to keep going up and down. The fact that there's gravity is a force applied to it, so now we also need to know what is the forced response. So this is kind of our natural and forced. And the first time I saw this, I thought the professor was just a glutton for punishment. Of just like, you took one seemingly easy differential equation and now we have multiple differential equations and I still don't know where you're going with this. But both of these are easier to solve because we can split them up. We can say the homogeneous is all going to add up to 0 and the particular is going to add up to everything else. So this has to be 0. This is going to be g, and then it satisfies the equation, right? 0 plus g is g. Or no, 0 plus g is not g. 0 plus g is g. Yeah, okay. Identity operation. 0 plus anything is still anything. My kids like to try to trick me with like math problems. And yeah, they're always like, what is like blah, 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 plus 0? I'm like, I don't know what you first said, but it's the same thing. Nothing happened. You did nothing. You've done nothing here. So that's all we did. We did nothing. We just said this whole thing is going to be 0. So xh, let's leave it as our a sine root 1000 times t. And now we need to figure out x double dot p plus xp is g. What is a function that if I take two derivatives of it and then add it to itself, I get a constant? This is a weird, like, conceptual problem. What do you think? E to the t. What do we think about e to the t? How would this work? No. Because I would end up with just 2e to the, then I would just have, oh yeah, I forgot the 1000, right? You still need to satisfy the original equation. can't just drop the constants. So I would end up with like 1001 e to the t equals g, and e to the t is never constant unless t is infinity, but we wanted to solve it for all time, not infinite time. So it's not that. What about just a straight line? No? Not gonna work? What is it? Do you already know? It's got, oh, it's gotta be 0? Or no? What about like a times t? Oh, I should use a different variable. Slope, s? S, like that? Slope times time? What's the derivative of slope times time? S times t. Slope, what's the second derivative of slope time, of slope? 0. So now I have 0 plus 1000 times st equals g. Does that work? Not really. Why do I say it doesn't work? So we're trying to figure out, like, for all time, for any value of time, is this true? Because remember, our equation of motion is true for all points in time. So if I'm saying s times t equals g, that might be true for one point in time. Yeah.
Whatever constant is 9.81 divided by 1,000 or whatever.
Yeah, we could just say that it's something, p, and then let p be g over 1,000. How's that? Second derivative of a constant function is 0, so now we're only dealing with g over 1,000, so that's our xp of t. So now we've got this. Single harmonic, yeah, simple harmonic oscillator. Spring SHM. How does this look? Are we done? Pretty close. Missing thing here is our we don't know what the amplitude is until we factor in the initial conditions. So it's called an iteration constant. So we'll start with our first initial condition, like when it hits a spring, we can call that 0, like position 0. What's a times sine of 1,000? What's the sine of 1,000 times 0? Sorry, square root 1,000 times 0. 0. And then plus g do with that? Zero equals zero plus g. G is zero, I guess. That makes sense. Gravity is just a figment of your imagination. It doesn't really affect anything. Something's got to be wrong with like that first guess, right? Because we can't say like that it's definitely a sine wave right now. What else could it be? Could be a cosine, right? It wouldn't change anything that we did when we were plugging it in. We would just have a sine and a cosine in there. So I can just add it in and it wouldn't actually change like that initial guess. Now, the only difference is now we have two constants instead of one constant, but we took two integrals. I mean, we didn't take integrals, we're kind of solving the integral by doing derivatives, which is a much easier way to do integrals in general, if you ever have the chance. It's easier to remember how to do a derivative than it is to do the integral. We can always do the derivative and then substitute back like what is the integral of it. So that's what we're doing here. So we'll add in here a plus b, and now we have another integration constant. Now we got one of our integration constants. I think we've solved like when we hit the spring, it's going about 3 meters per second. Is that right? Okay. So we know that at time 0, it's doing 3 meters per second. One derivative, we end up with that root 1000 times a cosine still end up with sines and cosines there. Sine is 0. Now A is that like speed over square root 1000, where that one's like the natural frequency, the natural response frequency. Now we have like a function and it's doing what we want. At time 0, it has an initial speed, 0 initial displacement, then it'll bounce down and come back up. And if we have position, then we can take derivatives, we can find velocity, we can figure out what the acceleration is. We kind of have like everything that we would want, whatever like terms we were trying to find, whether it's position, velocity, kinetic energy, potential energy, all those are kind of captured with position function. Not impressed. This is like, yeah, we did it. Second order differential. Okay, so we have like a solution to our equation of motion. This is like so what? What is that like? Was this worth the effort, or is this just an academic exercise that you have to do once and you should never do again? What's the importance of like this solution? So yeah, take a minute, talk about it. Like, why did we do this? Why do you want to know this? Why would someone want to know this? Why do we want to know this? Why did I tell you that you should know this? Like what's going on? Why would we do this? Why would we go through and spend like 20 minutes talking about well, what does that give us? Velocity? Okay, yeah, that's why I'm stopping here. Why would we want a solution to
Get back into it, you know?
yeah. I mean, like, different to the main goal is just to learn how to solve it.
Yeah.
So the solution is the goal. But here, like whether or not I have this answer doesn't matter. Like, this will help me understand what's happening or describe what's going on.
Yeah, we try,
Is
yeah, we,
this a predictive tool?
I suppose so.
Okay, maybe. You don't trust it, that's the thing.
I mean, it is really like a lot of,
Too much work.
yeah, so,
Okay.
but I don't know, I guess like my whole thing is like with the, especially like as you get more like complex differential equations, where you have like a lot of like changing variables, basically like the more dynamics that we're like looking for like
Yeah. I mean, that's what's happening here, right?
so it is helpful, yeah, helpful to
I'm glad I asked, because a lot of people were in asking the question, like, I don't know, why would we do this? So what do we think? Did anyone have a thought on, like, why would you go through this process? So, like in differential equations, the goal of the class is to solve differential equations. So it's very much the only reason you need the solution is because the solution is the solution you're looking for. But here, whether or not we need this one solution, I don't know. Like, is this like trying to pull diffie-q into a class that doesn't need it? Or is this actually helping us do engineering design? So what does like a solution to a differential equation give you that the differential equation is not giving you? Because we said f equals ma, and then do some algebra. Now a is negative k over m times x plus a g. Did it help us to go through this? It seems like I'm not convincing you. It seems like it's just extra work. One thought was like, it gives you a range of something. What's a range that this... That was a terrible star. There. What's a range that this equation gives us that we don't have in this equation? So here we have an equation of motion, second order diffie-q, and then there we have the solution to this diffie-q with the initial conditions considered. Is there a range here? Yeah? Yeah. Yeah, we have initial velocity, right? Yeah. You know what? I hate hand-drawn graphs anyway. Let's just... do I have... I think G over W, or I think W. Alright, so kind of taking like our function that we just solved and just plot it, like see what happens. What is like maximum position that we get to? Just like ballpark, you don't need 8.7, yeah, something around 0.65, 0.7, something like that. Minimum, what's gonna happen on the way back as the spring is like, because the graph is kind of flipped upside down, right? If we think about, we could put a negative sign if we want. As it goes down, and then what happens when it comes back up?
It stretches slightly above its regular state position.
Yeah, it'll actually like bounce back up a little higher than where it started. Not quite like, if there's nothing like binding it to the spring, then yeah, it would just launch back up. But if it hits the spring and it's like holding on to it now somehow, I don't know, a magnet or something, then this is kind of what it would do. Is it losing, so one of the thoughts we had was like, that it might lose energy, like somehow decreasing amplitude. But at least from the differential equation that we have and the solution that we got from it that solves it, there's no, amplitude's constant. It's always gonna go up and down the same way. Anything else that we know from it in terms of like design work? How long does the spring need to be? Yeah. Did you have something? Or just thinking? Just thinking? Okay. How long does the spring need to be? Yeah.
0.65.
0.65 if we,
Fully extended.
okay, yeah. So we need it at least as long as it's going to deflect, right? Maybe throw in an extra inch or two. Right?
Based on like these calculations, the object's never going to stop. There's no force causing this thing to stop oscillating.
Yeah, yeah. It's never, at least from our free body diagram, we have no forces that would cause this thing to stop. You know what? Let's just grab this. So that's like the plot of what we got. questions do we have about like? So to me, one of the biggest parts of this class is like being able to get to this equation. Whether you can go from here to here is like, there's lots of ways to get there. And today we looked at one of them, like just guess and check. You can tell a computer like, hey, this is my differential equation, give me an answer. And it doesn't give you a function, like it doesn't give you a function of t, but it'll tell you every position and every velocity for any point in time that you want. You can also use other like power series and stuff. So at least for this class, the main thing that I think we should get out of it is like, what is the differential equation? We need solutions to it, so we know like, is it a harmonic equation? Is this a damped equation? Like, so it's good to know like, what are we dealing with? But there's lots of ways to deal with it once we have that differential equation. You don't look convinced though. That's all right. We got time. Soon you'll just be like, yeah, more ODEs. Let's do it. Okay, thanks a lot. Pick up next time. We'll try the next step with dropping into the water. See what you come up with.